All right, welcome everyone. Today is Tuesday, February 19th, and we're going to cover lecture 7. Today we had a technical issue during the lecture, so the video was not recorded and it was corrupted. So I'm doing a rerun basically and recording it again. So it might be a little bit different, and I can spend a little bit more time on the exercise examples in the class, right? So let's see. Last session we covered CPU scheduling. We covered a few basic concepts of scheduling, the metrics that the schedulers are basically defined based on those, and also we covered some of the well-known algorithms in the scheduling. First come, first serve, shortest job first, and shortest remaining time first, a priority scheduler, and round robin. So, and we also talked about preemption, what it means to preempt a process by the scheduler, and then we learned how to draw Gantt charts and basically convert these algorithms against each other, pros and cons, right? So today, I'm going to first cover and ask if everyone has done their assignments. The deadline for a group submission and finalizing your groups has already been passed. If there is any missing groups, basically they should hurry up. It would be their own responsibility to get started with their project, and if you haven't done so, do it quickly. Make sure, this has been emphasized by the TAs, to follow the instructions as they are in those instructions that are on the piazza, because they are basically to avoid any other waste of time, your time and TA time. And if an instruction says that do it like A, that's to do it like A and not B. A lot of the times they might also be not intuitive. So for example, in the poll, it asks for your full name, but I specifically say please use your UBIT name. So that's to avoid, putting your name, so then I won't be able to, email you. So yeah, let's see. Today we're going to do a quick recap of the scheduling, and what we covered last session. And then we're going to talk about estimating CPU burst time, multi-level feedback queue scheduler, and 4.4 BSC priority based scheduler that you're going to implement in your Pintos project, number 1. So, first come, first serve scheduling algorithm. That is basically very simple to understand. Based on the arrival time of the processes, they come in a queue, and then the scheduler schedules the first process at the head of the queue on the processor, and then it just runs until it finishes, and then the next, and then the next. And basically, the pros is that it is somewhat fair, because once you are in the queue, you will have your own turn, but you won't basically starve. But the average response time can be lousy because of the combo effect, when short jobs basically wait behind a long job, or a process that basically keeping the CPU busy for a long time. And also it may lead to poor utilization of I/O, meaning if a process is on the processor and keeping the CPU busy without doing any I/O, the I/O is basically not doing any work. In the meantime, maybe there's a short process that it has a small CPU burst, but then it will wait for an I/O. In that case, you can use at the same time I/O and CPU, but because the CPU is only scheduling a long CPU intensive job, it won't utilize the I/O. Shortest job first was when a scheduler basically schedules the process which has the shortest burst time. And it is provably optimal with respect to average waiting time, and that basically prevents the combo effect. So the short jobs that come, they will get scheduled sooner, but then it can basically starve the longer jobs, because then all these short jobs can keep coming, and then the longer job is waiting for all of them. And also it requires the advanced knowledge of the CPU burst time. So this is difficult, this is not easy, and there's no way to basically know it. So there are ways to estimate it. We're going to cover it today. And shortest remaining time first is the same as this. It just has the preemption, meaning when a new process arrives, then the scheduler basically compares it against the currently running process. If the remaining time of the current running process is larger than the new process, then that will get scheduled, and the currently running process will get preempted. And there's no need to compare this against all the processes, because when a process is already running, that means that it was already shorter than the rest of the processes on the system, right? So when a new process comes, it is only required to get compared with the currently running. So if it's shorter, then we preempt this and then schedule the new one. If it's not shorter, then we just keep this running and then put that one in the queue. And so that's called shortest remaining time first. So priority scheduling is when we assign a priority to each of the processes, and that can be a constant number, or it can also be dynamic. It can be, again, an assigned integer at the start of when you create a thread or process, or it can change, or it can depend on other parameters. But when you define a priority, then you're basically assigning higher priorities to some of the processes than the others. And it guarantees early completion of high priority jobs that you don't want them to wait. Again, it depends on the system. So a lot of the times there are, for example, system processes that are of higher importance. For example, handling interrupts. If you don't handle an interrupt, in time, then it might just be lost. Maybe the data is, coming, and then you do process it and it will be lost. So, or another example is when you're in a car with self-driving or assistant, driving assistance. If there's a crash coming, then it has to engage the brakes, and you cannot postpone this, for example, to play the rest of the music or processing the sensors for tire pressure, right? Those are of lower priority. And the cons is that it can starve the lower priority. So if the higher priority process just keeps running, then it will starve the lower priority processes. And we also saw a couple of issues with priority inversion, and then the solution to that, which was donation in the Mars Pathfinder. So, but also how to assign priority to processes. We also saw that there is something called aging that basically changes the priority over time based on the dynamics of the process. So that can kind of solve the problem with starvation. So round robin is the next scheduling scheme, and in that basically we allow all the processes to get their own share of the CPU time. So they, one after another, they get a time quantum of the CPU time, and after they're done with that time quantum, they are put back on the end of the queue. The next process gets their own time. Again, when they're done, they go at the end of the queue. Now, so it's great for time sharing, and then there's no starvation, because again, you'll have your own share of time, and it does not require prior knowledge of the CPU burst time, because a scheduler just assigns CPU time to all the processes equally until they're finished. And it reduces the average response time, again, because each process gets a short burst time, so the processes in the queue will have their turn. But it basically increases the turnaround time, because all the processes are slowly progressing at the same time, so it increases the turnaround time. And the problem is with defining how the quantum should be. If it's too small, and then you're basically switching in and out processes so quickly that the overhead is too much. And if it's too large, the response time degrades. Basically, it will you're assigning too much time to one process instead of sharing the time. So this is the exercise that we had at the end of the last lecture, and along with the next slide. So we covered it in the class before the lecture of today, but since I'm doing a recording, so I will come back to these at the end of the lecture. This and this, right? So today, first we're going to talk about estimating CPU burst time, and that is for when a scheduler wants to estimate how much of a CPU burst time a process needs. And well, there's no way to actually know what it's going to be. What we can estimate based on their past behavior. So we can have a guess if a process has been using the CPU in short bursts. Maybe they're an IO intensive process, and they're going to behave the same way in the near future. But on the other hand, we can't just rely on some past. Maybe they change their behavior. So that's why we have to adjust our belief of the process. So in order to do that, we will use a moving averaging window. It's like exponential averaging formula. So we're going to take a look at this and basically try to understand what's going on. So this formula says that if we had a prediction of CPU burst for the nth time slot, and then during that time slot, the actual time it took for that process to run was Tn instead of tau n. We thought that it would be tau n, but it was actually Tn. We can have a better estimation, or we can adjust our estimation of the next time slot with calculating like this. So that would be our prediction for the next time slot. So there are three parameters in here. Tn is the actual length of the nth CPU burst. Tau n is the predicted value for nth CPU burst, basically before that happens. And then alpha is a number between 0 and 1. And this can, in this example, we're going to talk about it as a constant, but this can also vary. So what are we basically talking about here? So if you look at here, we are assigning a weight to our previous prediction, which was basically a belief based on a previous history of the process. And then we are also assigning a weight to the most recent behavior of the process. And because this can be very different than this, it can be similar. But now there's the different weights. So it depends how much we want to care about the most recent behavior or basically the history of the process. So let's take a look at the extremes. If we take alpha to 0, then this part is 0. It will basically be gone. And then this will be 1. So tau n plus 1 is exactly equal as tau n. So if alpha is 0, that means our prediction will be regardless of the actual behavior of the CPU and whatever that we had predicted before, then we're going to predict the same thing. So we're not going to change our belief of the process behavior. If alpha is 1 on the extreme, this term will be 0. We forget about the history of the process altogether, and whatever that the process did in the last burst, we're going to predict that it's going to be the same in the next burst. So these are the extremes. So alpha is basically how much we are caring about the most recent behavior of the process and how quickly we're changing our belief of the process behavior. So if we thought that it's a short burst behavior and one burst the process now takes a long time, then quickly we change and then we change our belief. Okay, now this is taking a long time, so we predict it's going to take a long time, right? So this basically summarizes that. If alpha is 0, it's going to be the same prediction. If alpha is 1, the prediction of the history is basically gone, and then we're going to we're going to predict the same as the most recent behavior. So where is that? Okay. So if you want to expand this formula, take a look at this. You don't have to do all the math, but it's just to understand. So this was the initial term. Now the tau n itself is calculated the same way, right? So if you basically expand tau n to alpha t n negative 1 minus alpha t n minus 1, tau n minus 1, right? So this is this. And then now you multiply this 1 minus alpha into and break this parenthesis. So 1 minus alpha multiplied by alpha t n minus 1, and 1 minus alpha goes into this, gets to the power 2, and then this, right? So you can take a look, and then basically again the Tn minus 1, we can expand it further and further, and then basically the full expanded term look like this. So alpha Tn, 1 minus alpha, alpha Tn minus 1, 1 minus alpha to the power 2, alpha Tn minus 2, and so on to the tau 0, right? And there's only one constant there, and then that is tau 0. Initially, without when the thread or process was created, we had we had a guess, or we had a constant value. That was tau n. After that, based on the next time slots of the process on the CPU. Now we're predicting. So let's take a look. Every time it's alpha multiplied by the actual, t, but also 1 minus alpha is like, increasing as we go into the past. And because alpha is between 0 and 1, and 1 minus alpha is also between 0 and 1, that means each term is getting a smaller weight. We are multiplying this by 1 minus alpha, which is less than 1. So that gets smaller. That gets smaller. And then this is the smallest, right? And that means that basically our prediction is taking into account the more recent behavior with more weight. And we are caring less about the past history, like a far history, right? And basically the alpha now changes these weight, how quickly this exponential term is damping, right? If the alpha is high and close to 1, then it will damp basically very quickly, because 1 minus alpha is, almost 0. So it damps quickly, and that means we are only caring about very recent history. If alpha is close to 0, basically this term will be smaller, and then this will be closer to 1, this will be, it will still be less than this one, but it will damp smoother towards the past. Meaning we still care about, past history quite a bit. We don't change our opinion just based on, a couple of last slots, right? So this actually shows it in a diagram. So in this case, the alpha is like 0.5, and the initial tau 0 is 10, right? And the actual burst of the CPU time, let's consider them to be 4 milliseconds, and then 13 milliseconds, and so on. And our initial guess is tau 0 is 10, and then basically it tries to adjust, because this is less than this comes down. This comes down, and then here it crosses, and then it wants to adjust itself again. It goes up, and so on. So it kind of smoothly follows, but also predicts. So it predicts the next few time slots based on the previous history, and then as it sees the changes, it can adjust itself. So this is an example. Consider the exponential average formula used to predict the length of the next CPU burst, and what are the implications of assigning the following values to the parameters used by the algorithm. So when we talked about it here, so when alpha is 0, basically we don't care about the most recent behavior, and we are basically rigid in our, whatever that we believe of the process. So if initially we thought that it would take 100 milliseconds during next burst, we're going to keep predicting that. If alpha is almost close to 1, which is 99, it doesn't matter like what we predicted initially. We will basically be too agile and change our opinion of the process very quickly, and just follow whatever the previous burst was, and we're going to predict that's for the next burst. All right? Basically, we say the prediction is almost memoryless. We don't take into account the past history. All right? So we're going to go and cover the multi-level feedback queue scheduler. So about these two, we talked a little bit in the lecture number 5, project 1 discussion session, and we're going to talk a little bit more in depth. So what is a multi-level queue scheduler? It has multi-level queues, and so that means, like, for example, we have a low priority, middle priorities, and then high priority, but there are multiple queues, meaning the processes in this queue are not compared with the processes against this queue. And so this example shows if you have a higher priority system processes in this one, and then maybe you have a batch process here, as long these won't basically intervene each other's scheduling. So the scheduler picks between the system processes in one scheme, and then chooses in one scheme, and it also has a different algorithm when to pick a process from this queue, when to pick a process from this queue. So in this case, for example, it's defined by a priority. So if you have higher priority processes, then basically you only pick between those. If you don't have those, then you go to the next queue, right? So a multi-level feedback queue scheduler has the feedback keyword, meaning we basically get a feedback from the process behavior or other parameters that dynamically will change where we put the processes. So we can basically move the processes from one queue to another queue. In the previous example, we can bring down the priority of a process or increase the priority of a process based on, again, it can be based on the behavior of the process or behavior of the scheduler or the events, external events. So a multi-level feedback queue scheduler basically is defined by the parameters. So the first of all is number of queues. So in the previous example, we had 5 queues. And then scheduling algorithms for each queue. So within each queue, how are we going to choose the processes? Are we going to do round robin? Are we going to do first come first serve, shortest job first? Any other algorithm that we have talked about. Methods used to determine which queue a process will enter when that process needs service. Meaning, when a process arrives, for example, we have to put it in one of the queues. How to know which queue it should initially go? How to know? So in this case, for example, we can kind of tell if it's a process that is created by the student, then it goes into this. If it's a process that is interactive, based on some definitions of the process, it goes into this. If it's a system process, it goes into this. But in general, there should be a method to determine this. And then there are methods used to determine when to upgrade a process, move it up into one queue, or move it down the queue, right? So these are required for a multi-level feedback queue scheduler or MLFQS. So this is an example of MLFQS. So we have 3 queues here, and basically when a process enters, it enters this queue, and it gets a short burst of 8 milliseconds of time of the CPU. It's a first come first serve, so it's round robin basically, but you don't get to go at the end of this queue anymore. Once you get the process is assigned 8 milliseconds of the CPU, if it's not finished, then it will be basically moved to the next queue here. And then in this queue it will wait until it is assigned, and then it will take 16 milliseconds of the CPU burst time. If it's done, then it's good. If it's not done, then it goes to the lower queue and then waits there. So in this case, if one of these processes gets scheduled on the CPU, it will just keep running until it's finished. Now, in this example, it basically is quickly giving a response to any new process, and if they're short, they quickly will get finished. If they're not, then they move down, and again, these can be considered as medium processes that they got their first response here, maybe they were not finished, maybe they were waiting for something, and then they will get a second quantum a little bit longer, and then, if they're not finished, then go into this maybe lower priority. So considering, we have to schedule between this queue or this queue. So maybe this has higher priority. So if there is a new process, we quickly give it 8 milliseconds of time. Every now and often, we go and pick some process from here. And once the system is not busy anymore, we pick this one from here. Right? This is an example. So now we're going to go to the 4.4 BSC priority basis scheduler, which is what you're going to implement in the Pintos project number 1. So in the BSC priority basis scheduler, the priority actually goes up as the number increases. This is unlike what we have covered in the lectures or it's in the book. So in this scheduler, the priority 0 is actually minimum, and the priority 63 is maximum. There are 64 queues. Each of these priorities is a queue. They can contain 0, 1, or many processes, right? And so in this case, for example, it's represented as similar to a linked list. But if there are processes in this priority queue, then this is a priority-based scheduler. Meaning, if there's processes with priority 6, none of these processes should be scheduled. Now, if there are multi-processes here in the with priority 6, now you do them with like round robin. So once this priority gets finished, then you look at the next queue. So basically, from the highest priority, you have to take a look at the queues. The first non-empty queue you have to pick and round robin the processes within that queue. And again, if there is no process, then you take a look at the next highest priority queue. Okay. And so how to calculate priority? In this case, the priority is not going to be constant. It actually needs to be calculated because it's dynamic. So every 4 clock ticks, remember in the PINTOS, there is a timer tick, which basically depends on the frequency of the timer. So the faster the frequency of the timer, the shorter each tick is. In the PINTOS, the timer frequency is 100, so each timer tick is 10 milliseconds, but it does not matter that much. So every 4 clock ticks, you have to calculate a priority, which is like this. A priority is priority max minus recent CPU divided by 4 minus nice multiplied by 2, rounded down to the nearest integer. So let's take a look at what's happening here. So we are taking a priority max, and then we are basically taking some numbers off it. And these numbers, the nice value we're going to cover in the next slide, and that's basically a constant. And then recent CPU is roughly how much the process has occupied the CPU recently. So this basically will change its priority. So if a process is keeping CPU busy recently a lot, we're going to push it down the priority and say, okay, you've been keeping CPU too busy, now maybe we should let other processes know. Vice versa. If a process is not getting scheduled, recently, we're basically bumping it up, and then we're going to allow it to get scheduled, right? So this basically is the way that we define our aging solution. And the nice value is a constant, right? So the nice value is a constant that is defined initially with when a thread is getting created, and it basically tells how nice or this thread wants to be to other processes. It's kind of like manners. So if a thread has a nice value up to 20, it means that because it's getting subtracted from this priority max, it's going to basically decrease it, right? So the more nice a process is, that means the more manners it has, the more it tends to back off and then let other processes get scheduled. And the less nice it is, up to a value of -20, it's that this thread is kind of like mean or aggressive and wants to get other threads' time. And well, you might say, okay, why a thread should be nice to the other threads? This is usually not set in the user space; it's set in the kernel space. So kernel can decide how nice a thread should be, right? Or maybe depending on some events, you want to change this. But regardless, it is part of the implementation. So the recent CPU is what we talked about, and that's basically going to cover how much a process is occupying CPU time recently. Well, what you can do is just add up the CPU bursts, but for that, for each of the threads, you have to have n time slots and measure each of them and save them in the queue, and then add them up every time that you want to calculate this, and that takes a lot of space and time. And that's how to do it accurately, but we don't actually care. We don't want to know exactly how much it has occupied the CPU. We want to have an estimate or roughly tell it. So that's why we're going to use the same principle of the exponential averaging, right? So again, if we have a prediction of recent CPU for the T-1 slot, then we're going to update our recent CPU based on that. So what we're going to do is every tick, we're going to, at each timer interrupt, every tick, we're going to increase the recent CPU of the running thread. For the other threads, they're not running, so their recent CPU doesn't change. For this running thread, the recent CPU will increase by 1. Now, once per second, meaning when the number of ticks divided by the timer frequency has a 0 remainder, you recalculate this for every thread, even for the ones that are not running. Because if they're not running, well, the recent CPU overall should kind of decrease. And for the running thread that has now increased, we now update based on the same principle. So the nice value we already talked about, it's a constant. And then you basically multiply the recent CPU by a number. And that number is a fraction between 0 and 1. It is very similar to the alpha that we had before. So it's the number 2 multiplied by load average divided by 2 multiplied by load average plus 1. So this fraction is between 0 and 1. But it's not constant. We're going to talk about it in the next slide. So alpha is again between 0 and 1. It's going to like basically dictate how quickly we should adjust our belief of a process and basically take the recent CPU time based on their most recent behavior or their past. And so we're going to use that alpha in this. And before going to the next slide, I'm going to basically tell what it means. So alpha is basically being calculated based on a load average. So a load average is a rough estimation on how much, like overall on average, how much is the load of the system. So if we have many processes on the system or many threads on the system, our average load is up. If we only have like a couple of threads, our average load is low. Now, why does it matter? Let's take a look at how it's defined here. If the load average is small, then this number is closer to 0. Let's say, like if the load average, for example, is 1, then we have 2 divided by 3. If load average is up, if it goes up, let's say we have 100 threads on the system, then it will be 200 divided by 201, which is much closer to 1. And that basically tells us if we don't have to, if we don't have a load on the CPU, then alpha can be lower, meaning it can be more smooth. If you remember the exponential average, the smaller the alpha, it can move smoother. It can basically adjust itself to the recent behavior of the process slowly and not change its belief of the one process behavior in the past. Whereas when alpha goes up, it will take into account the recent behavior more importantly. Now, why we should care? So if the load average is up, meaning we have a lot of threads, we don't have time to let ourselves to adjust to the behavior of the threads. So if a short burst process now has become a long burst or CPU intensive process, we have to quickly adjust ourselves and then basically act upon this because other threads are, waiting for CPU time. So we quickly adjust our belief of this process so we can, schedule the other ones. So that's why when the load average increases, we basically take into account more of the recent behavior. So the load average is calculated like this. It will be initialized to 0, and then once per second, again, we'll basically count the number of threads and then multiply that by 1 over 60, and then whatever that we had for our previous load average in the last second, we're going to multiply that by 59 over 60. So again, roughly it will tell us how many threads we had in the last minute. This itself, again, has the same behavior as exponential averaging, and it roughly will tell us how many threads we had on the system during the last minute. So every second, the ready threads will update this value, but only with the weight of 1/60. And so this is also important. So recent CPU is specific to a thread, and priority is also specific to a thread, but alpha and load average, they're system-wide. So now during your implementation of your MLFQS, basically you need to every tick you do something, which is updating a thread recent CPU, but every second there are system-wide things that you need to do. You need to calculate the load average, you need to calculate alpha, then you need to update recent CPU for all the threads. Okay. And another thing is that if you take a look at the priority and the priority and recent CPU, or in this case, there are integers. But the load average and alpha, and when you want to also calculate the nice value is integer, the priority is integer, but the load average, this A here, and the recent CPU, they will basically be floating numbers, right? So A is floating, you want to multiply it by a number that will have floating, or you have to convert it basically to integer. And why does it matter? You have probably had experience with floating numbers, with double or real floats. So it matters because floating numbers are not supported in the kernel, in the Pintos kernel. The reason is, in order to support floating numbers, they're usually slower, and that slows down the kernel. So instead, you have to basically implement floating multiplications, addition, subtraction, and division by using integers. So this is actually a part of your project number 1. So if you take a look at the Pintos documentation, you'll see this, that you have to implement at the end of reference, I think B, where the 4.4 BSC scheduler is defined. At the end of that, there's a simple explanation of how to approach this implementation. You have to basically represent a number using integer values, but differently. And then now if you want to do a subtraction, any math operation with using the float numbers, you have to implement it using these integers. So this integer is now representing this floating number, and this integer is now representing this floating number. Whatever that the multiplication of these floating numbers should be, you want to implement it using these integers in a way that the representation results represent the actual multiplication. So this is actually again part of the implementation of project number 1, but we will actually provide you with this because the implementation actually takes some time and understanding, and it is actually worthwhile to understand how to do this, but it does not help you a lot for operating system knowledge. So we're going to provide the students with a header file, which is a fixed point header file, and this is going to have a few transformations. So if you give it a number, it will give you a number which represent a floating number, and then you have some functions that do addition, subtraction, multiplication, and division, and then again you have transformation back to the integer version, right? So make sure when we put that on Piazza, you download it and put them in your code. So for next session and for your recitation, basically, make sure that you read these files completely and understand them. You should understand what are the data structures defined there, what are the variables, what are going to be used for, what are the functions, where these functions are called, from which file. Basically be able to move from this file to the other file and knowing where you're going, where you're reading a function. Now there's another function called, you should know where this function is defined so you can navigate to that code and understand what's going on. So thread.cnh, timer.cnh, which is in the devices, mostly again with the not the initialization of the timer, but mostly with the where the timer is, the tick is happening or the thread timer is increasing. Init.c and init.h, again, roughly being able to follow the boot procedure and where the kernel gets its argument then for tests. Interrupt.c and .h, again, mostly for the timer interrupt, not, other interrupts, but the timer interrupt. Sync.cnh, this is very important. You're going to use it for semaphores and locks. We're going to cover the concept of synchronization, race conditions, semaphores and locks in the next couple of lectures. But for you to understand how it is implemented and used in PinToast, it's important. List.cnh, they are in the lib/kernel/directory. And this is really important. You're going to use them. And you're going to basically understand how the implementation of list in PinToast works. And then you're going to see how this list is basically, for example, used in sync, in semaphore lists. And that will give you some idea for your implementation. All right? And also, for next session, we're going to talk about process synchronization, so you can start reading chapter 5. So, this, today we covered, we did a recap of a previous session, and also we covered estimating CPU burst time, MLFQS, and 4.4 BSC priority-based scheduler, which you're going to implement in your PinToast. All right? So, now at the end of this, I'm going to just bring up the screen and go on to the couple of exercises that we had. Right? So, the first exercise, how we want to approach these exercises is to basically be very accurate, note down, and then trying on a couple of papers on the draft, making it everything. Try not to memorize numbers the remaining time. Try to write everything down and approach it chronologically. So basically start at time 0 and then basically whenever an event happens, just like follow that. And at the end, make sure you double check, right? So for this, let's take a look. I'm going to push the screen up and do it on the blackboard. So the first thing is that we're going to draw a chart of the information. So we have been given as shortest remaining time first algorithm, and we have 5 processes: P1, P2, P3, P4, and P5, right? And now we have been given their arrival time, 96875, 34597, 34597, and that is burst time. And then we've been given 54321 for priority. So it's important to know again, usually in our examples, the lower the priority number, the higher the priority of the process is. So in this case, for example, if we want to basically schedule them based on priority, this has the highest priority. But it's the shortest remaining time first. This is the first thing that you're going to notice. So in the shortest remaining time first, we don't care about priority. So in this example, we're actually not going to use this at all. And then we've been asked for response time. Wait time. And turnaround time. Okay? So, I'm just going to push it up, and again, as we did in the class, I'm just going to do it on this one. Okay, that has a nice curve. When you're drawing the Gantt chart, start at time 0 and then see what's going to happen. Make sure you have the arrivals. And in this example, we are doing a shortest remaining time first. So we have to keep track of the remaining time of the processes. Usually the preemptive schedulings are a little bit more difficult because at each arrival of a new process, we have to reevaluate. So pay more attention to those, right? So at time 0, nothing's going to happen because there's no process ready yet. Okay? So I'm just going to write it down here, P1. P2, P3, P4, and P5. So, at time 0, we have no information about any of them, right? And this goes on until 5th millisecond, where process number 5 arrives with the burst time of 7. So I'm going to write down 7 here, no information about anything else yet. So at this point, at time 5, we're going to schedule, so before this, the CPU is like idle, and then we're going to schedule P5 here. And so it's going to run either till it finishes, so it has 7th burst time, or if anything else happens. Is there anything else happening? Yes. At time 6, 7, 8, and 9, we'll have arrivals. So let's write them down here and then figure out. At time 6, what happens is P2 arrives with the burst time of 4. So we update this with 4. This one is still no update. This one no update. This no update. This one has run for 1 millisecond. So this will move down to 6. The remaining time of this process is 6. This process has arrived with remaining time of 4. So since this is smaller than the current process, we have to schedule this out, preempt it, and put this one on the process. So process number 5 is scheduled out, and process number 2 will get scheduled in. So it will run again for 1 more millisecond till something happens. So at time 7, P4 comes with the burst time of 9. So I'm going to write it down here. This was scheduled out, so it's going to just stay the same. We don't have any information of this. This kept running for 1 millisecond, and then no information on this. So at this point, the P2 is running. Remaining time 3 milliseconds. A new process comes, 9. It's larger, so we don't have to schedule this one. We just let this one run. So it will run for another millisecond till 8. At 8, another process comes. Process number 3 with burst time of 5. P2 has run for another millisecond, so now the remaining time is 2. No information, no change. Again, since 5 is larger than 2, we don't have to preempt this, and then we'll let it run. At time 9, process number 1 comes with burst time of 3. So now we have a process number 3, process number 1 with burst time 3. The remaining time of P2 is 1. The rest has no change. So this is still smaller than this, right? So we let it finish till 10. So this will run till 0, and then now it's gone. So once it's gone, we basically write everything else down and then take a look. So which one is the shortest now? Is 3. So from here on, the shortest remaining time and shortest job first is basically equal because we don't have any more arrival. And so when a process starts, it just runs it till it finishes. So when P1 gets scheduled because it has the shortest time, it just runs for 3 milliseconds until 13, and then it will turn to 0. And then here we have 5, 9, and 6. So the shortest one is P3 with 5 milliseconds. It runs for 5 milliseconds till 18th. And then basically it will finish. Now again we have 9 and 6, so 6 is smaller, so P5 will get scheduled for 6 milliseconds up to 24, and then this will turn to 0, and then this is our only process now, so this will get scheduled P4 and then runs for 9 milliseconds till 33. Okay, so double checking. The first thing that you can do to double check, the first thing to do to double check is to add up the burst times and see if it's right. So the burst times are 3, 4, which is 7, 5, 12, with 9, 21, with 7, 28. So the CPU should be busy for 28 milliseconds. Well, we have some idle time, so we also have to add that. So 5 plus 28, that's 33. It seems right. Next, look at each of the processes' burst times and add them up. So for example, P1 burst time is 3. Where is P1? Here, from 10 to 13, that's 3, that's correct. P2, it's 4. From 6 to 10. This graph is not in proportions, so it's fine. When you do it, you can do it first on a draft and then draw it more nicely or more proportional, but sometimes it doesn't matter. As long as you have the numbers here, that's fine. So it is actually running for 4 milliseconds. P3, 5 milliseconds. P3 here from 13 to 18. Although basically we got these numbers because of that, you might make a mistake. So you always double check from a different way. P4, it should run for 9 milliseconds. Again, recalculate, 9. P5, it has to run for 7 milliseconds. Well, here it has run for 1 millisecond. Here it has run for 6 milliseconds. Add them up, that's 7, and that matches. So let's now calculate the timings: response time, wait time, and turnaround time. So the response time is the first time that the process is waiting, meaning from arrival time till the first time it gets scheduled on the CPU, right? So for P1, it arrived at 9. When did it get scheduled? 10. So the response time is 1. And for P2, it arrived at 6. When did it scheduled? At 6. So the response time is basically 0. For P3, it arrived at 8, and we got it scheduled at 13. So the response time is 5. For P4, the arrival is 7, and we got it scheduled at 24, so that the response time is 17. For P5, we got it arrived at 5, and we got it scheduled at 5, so basically, again, the response time is 0. Now, for wait time, the wait time is the total amount of time a process is waiting, and that includes the response time. So, in case of P1, for example, when P1 is scheduled, it finishes, right? When it gets scheduled for the first time, it runs until it finishes. In this case, the response time and wait time are equal, because whatever it has waited for the first time, that's the only time it has waited. Same goes for P2. P2, when it's scheduled for the first time, it's running all the way till it finishes. So the same happens. For P3, again, it has happened. So the same number. For P4, again, once it gets scheduled, it just kept running, so the same. For P5, however, the first time it didn't wait, but then it had to wait from 6 all the way to 18 to get rescheduled and then finish. So now it has another 12 milliseconds of wait time. Now, the turnaround time, you can calculate it 2 ways. The turnaround time is from when the process has arrived until it finishes. And you can basically calculate it 2 ways. One way, I do it usually this way, is easier, is to take a look at when it finished and then subtract when it has arrived. So for example, for P1, when did it finish? At 13. When did it arrive? At 9. So that's 4. 4. P2, it finished right there at 10, and it arrived at 6. So again, it's 4. Now, the other way to calculate this is, remember, from when it arrived till it finishes, a process is either waiting or getting service. The total amount of service time on the CPU is the burst time. That's what we call, right? And the total amount of wait time we have already calculated. So we can just sum them up too. See, 3 and 1 is 4. 0 and 4 is 4. 5 and 5 is 10. 9 and 17 is 26. 7 and 12 is 19. Now, it also kind of helps if you calculated it both ways and compare. So, for example, we made a mistake, then we figured it out. We actually did this and we realized, oh, these two ways don't match up. And then that caused us to redo or figure out or pay more attention and find our mistake, right? So in this case, we can calculate these as well. So for P3, it finishes at 18 and it started at 8. So then it subtracted, you get 10. Okay, it's the same. For P4, it finished at 33. It arrived at 5. So you subtract that and then it arrived at 7. Subtracting it from 33 will give you 26. See, if you have a neater table, you might not make a mistake. So P5, it finished at 24. It arrived at 5. Again, you subtract it and you get 19. So this is going to be this example. All right. So, and if you want to calculate the average turnaround time or average response time or average wait time, basically you sum them up and divide them by the number of processes. So in this example, it's not needed. Before moving to, okay, this is, and this is what I wanted to show about the turnaround time. I can actually show it here. So from arrival till a process is finished, right? You have some wait time, some service time. Some wait time, some service time. It's either this or that. There's no other way, right? So if you sum the service times, which are the burst times, and sum the wait times, that will be equal to turnaround time. If you take the finish time and subtract the arrival time, you should get the same number. If these numbers don't match up, then that indicates a mistake somewhere. And remember, the first wait time is also called the response time. So when you are calculating wait time, you should make sure that you include that response time as well as other wait times between the services. All right? So okay. Bring it on the screen. So the next example is this one. So it asks to draw the Gantt charts, find average turnaround time, waiting time, response time for each processor for each of the first come first serve, shortest job first, shortest remaining time first, round robin with a quantum of 4, priority, preemptive and non-preemptive. So this basically includes all the types of the scheduler, and this is a good exercise for you to make sure you do them. This example with this arrival time and the process burst times, they don't cover, all the situations that can happen. You have to, for example, watch out for the idle times. You have to watch out for the ties that you might need to break. But this is, again, a good exercise for everyone to do that. So again, I'm just going to write down the chart. So we have, I try to have this one a little bit nicer. Arrival, we have burst time. This one we have 4 processes. So we have priority, and then we have response time, wait time, turnaround time, okay, so P1, P2, P3, and P4. So the arrival time is 0, 5, 10, 15, 0, 5, 10, and 15. And then the burst time are 20, 15, 10, and 5. And the priorities are 3, 1, 2, 4, 3, 1, 2, 4. And the quantum is also 4 in case we are doing it for a round robin. I'm just going to write it down here, somewhere in the corner, right here. Quantum is 4. Right? So, as we did in class, I'm going to do it with round robin. Actually, I'm just going to write it here. And then after this, we might be able to also cover a couple of other examples since we're doing it outside of the lecture time, which is good. All right. So, since round robin has a lot of preemptions, we can have, depending on the burst times and time quantum, it is one of the scheduling algorithms that you might make a lot of mistakes. Again, in class, for example, we did one. Try to take your time and be clear on your paper, even on your own draft. Usually, the questions that you solve, they're not time intensive. I mean, time challenging. So you have your own time. Make sure you spend the time. As you saw, once you get the Gantt chart, then you basically fill a lot of, solve all the response time, wait time, and everything. So if you get the first one wrong, then the rest of them can also be incorrect. So make sure, the first Gantt chart at least, you make sure the scheduling is correct with no mistake. You double check, and then the rest will fall in place. So, so the first thing first is again have an idea of how long everything's going to take. So burst time is 20, 15, 10, and 5. So the overall it will take 50 milliseconds, considering there will be no idle time. We don't know that, but at least we know when we want to divide this bar, it has to go all the way to 50. So if you're 10 and then you're here, then you're going to probably end up with tightening up and writing down in the corners, whatever. So let's start at time 0 here. And now if we want to do round robin, remember because each process is taking some of the CPU time, there will be some remaining time that next time you need to calculate, because even though the quantum is 4, now maybe the remaining time of the process is 3, so then the quantum will finish there. So you have to all, take them. So what we're going to do is I'm going to write remaining time here. And actually, I'm going to, again, like what we did in class, I'm going to basically represent the round robin queue as time goes by. This is all going to be very helpful in the round robin one. So when time 0 hits, the P1 arrives. What is the burst time? It's 20. So at this time, it will be P1 with remaining time of 20. That is what the queue looks like. So because it's the only process, it will get the time quantum. The P1 gets scheduled. It runs for 4 milliseconds because it wants to run for 20, but we can only give it 4 milliseconds, so it will run till 4. I'm going to actually draw it a little bit tighter, like this. At time 4, P1 goes at the end of the queue with the remaining time of 6. We haven't scheduled it out yet. So this line is not necessary, but you have to evaluate this. So P1 is in the queue with 16, and by the time 4, well, nothing else has happened. So it gets another time quantum, and it runs till 8. At 8, P1 is 12. By this time, P2 has arrived. P2 has arrived here, and it goes at the end of the queue, right? So P2 arrives with the time with the burst time of 15. So at 8, because P2 is in the queue, P1 will get scheduled out and then go at the end of the queue. So the queue will look like P2 with 15 and P1 with 12. And now P2 will get scheduled and P1 gets preempted. P2 gets scheduled for, it wants to run for 15 milliseconds. We give it 4 and see what happens. So, time 12. Before this time happens, P3 arrives at time 10. So at time 10, P3 arrives. So when P3 arrives, it goes at the end of the queue, right? So at this point, what is it? Like P2, P1, and P3. I'm writing P2 here just to make it clear. Basically, P2 is already scheduled. So, you know, it's up to you what you write. It just like matters that you keep track of the remaining time, the burst time, the order of the processes in the queue. It's not part of the Gantt chart. This basically, this is you know. So at time 12, because P2's turn is over and there are other processes in the waiting, so P2 goes at the end of the queue. I'm gonna write the queue here. So it's gonna be P1, P2, P3. So P1, P3, and then P2 goes at the end of the queue, and then P1 gets scheduled. So by this time, well, P1 has 12 time remaining. P3 has come with the burst time of 10. P2 remaining time is 12 minus 15 minus 4, so that's 11. So P1 gets scheduled for, it wants to run for 12, but it will run only for 4 milliseconds till 16. But before that, again, something else happens. By time 15, process number 4 arrives, and with the burst time of 5. So then it will go basically at the end of the queue. So then the queue will look like P1, P3, P2, and then P4. The burst time of P4 is 5. P2, 11, has not changed. P3 is 10, has not changed. P1, we're going to calculate. At 16, we need to basically preempt P1, put it at the end of the queue. So P1 started at the 12. At the end of 16, the burst time is going to be 8, and it will go at the end of the queue. And then P3 will get scheduled. So the queue will look like P3, P2, P4, P1. P1 has reduced to 8. P4 is not changed, 5. P2 is not changed. P3 up to this point is 10. And then we're going to start. So from here on, it's a little bit easier because we don't have arrival, so we don't have to basically change the queue in the middle of the quantums. it's just going to be either the quantum time or when a process finishes, right? So for example, P3, it was to run for 10. Well, it will run only for 4. So we already know at time 20, now the queue looks like this. P2 with 11, P4 with 5, P1 with 8, and then P3 with 6. Even at this point, if you don't want to continue and then end up with a problem, if you feel that it's taking quite a bit of time or you're not confident, you can stop and double check everything, especially the numbers, right? So for example, P1 had a burst time of 20. So let's see what have we done. So we scheduled this for 2 quantums here, so 8 milliseconds, and then for 4 more quantum milliseconds here. So that's a total of 12 milliseconds. Initially 20. Now it has been serviced for 12 milliseconds. So the left time should be 8 for it. Have I done it? Yes. P2. The burst time is 15. So it got scheduled here for 4 milliseconds. So now it should be 11. Is it there? Yes. P3. The burst time is 10. It got scheduled for 4 milliseconds. So now it should be 6. Is it? Yes. And P4. P4 arrived 15. It had the burst time of 5. Well, we have not scheduled it yet, so the burst time is still 5. It's in the queue and waiting. How about the orders? P1, after P1, P2 arrived. I mean, we figured out how the queue was, but we got a schedule after P2. By this time, P1 was waiting already, so P1 went there. P3 arrived, and then, it was before P2 got finished, so after P1, it would be P3 before P2. So at least, you kind of like recheck this so that you end up, with a problem that then you have to fix a lot. Because again, if you make a mistake here, then the rest of the Gantt chart will be wrong. So far we've got it right. P3 is at the end of the queue here. P2 gets scheduled for 4 quantums. 11 wants to run, so it will run to 24. And then it will go at the end of the queue. So P4, P1, P3, P2 with 7. The others you can again keep writing so you don't make a mistake. It's going to be 8. P4 is 5. So now P4 gets scheduled. Again, it has more than 4 service time. It requires more than 4 milliseconds of service time, so it gets the whole quantum till 28, where it basically goes at the end of the line. It will be P1, P3, P2, P4 reduced to 1. I don't write the ones that has not changed. So P1 here is 8, and that just goes on there for 4 more milliseconds till 32. And here again it goes at the end of the line. So the line will look like P3, P2, P4 and P1. Now it has changed from 8 to 4. Okay? If you want to write down the other ones, they're still the same. So P4 is 1, P2 is 7, P3 is 6. So when P3 gets scheduled here, again, it wants to run for 6 milliseconds. It only gets 4 up to 36. I'm going to again write it a little bit tighter. 36. And by the end of 36, it goes at the end of the line. How the line looks here, push it a little bit up. P2 with 7, P4 with 1 only, P1 with 4 milliseconds, and then P3, which was 6, but now is only 2. Okay? So here P2 gets scheduled. It runs for another 4 milliseconds, up to 40. Let me just clear this up too. It gets 4 more milliseconds of service, and then it goes at the end of the line. So now we have P4, P1, P3, and then P2, which was 7, but now will be 3. The rest has not changed. 2, 4, and 1. So here you should make, for example, it's the first time that the time quantum will be actually over sooner, because P4 P4 wants to run for only 1 millisecond, even though it can take 4 milliseconds, but it only runs for 1 millisecond. So it runs only till 41. And then it will finish, right? So I'm just going to cross it out. And the rest of the queue will look the same. And so from here, the time quantum is not necessarily multiples of 4. It's from whenever the quantum starts, then, the process gets at most 4 milliseconds. So the next quantum, P1, gets scheduled here, and it runs for 4 milliseconds starting from 41, and then in this case, P1 finishes at the end of its own quantum, so, at time 45, P1 gets finished, and now the line looks like, you can also rewrite the whole queue if that helps, but it's the same. So then the P3 gets scheduled, and it requires 2 milliseconds. Again, that's less than a quantum, so P3 gets scheduled till 47. And then in the end, P2 has 3 more milliseconds, so P2 gets scheduled till time 50. As expected, they ran for 50 milliseconds. We didn't have any idle time, so everything looks fine, right? So now, if we want to double check, you can check with the arrival time, the service time, burst time, and everything. Again, add them up. So, for example, the P1, it has to have 20 service time altogether. So P1, there is 8, and then there is 4, and that's 12, and there is another 4 over, that's 16, and there is another 4 over there, which makes it 20. P2, burst time is 15. We have a 4 over there. We have a 4 over there, that makes 8. We have another 4 over there, that's 12, and we have a 3 over there, that makes 15. Just as simple as that. You do it, and then again, you won't regret it that you put this time. P3 should have a burst time of 10. Don't read the chart, the table. Make sure you're paying attention. So 10. P3. We have a 4 over there. We have a 4 over there, that's 8, and then we have a 2 over there, that's 10. P4 has a burst of 5. We have a 4 over there, and then we have a 1 over there, so that's 5. So they seem to be fine. What about the response time? The response time for P1, it arrived at 0, it got scheduled at 0, so the response time is 0. P2, it arrived at 5, it got scheduled at 8, so it's 3. For P3, it arrived at 10, it got scheduled at 16 for the first time, so the response time is 6. P4, it arrived at 15, and it got scheduled at 24, so that's 9. Wait time, response time plus all the other wait times, right? So, process number 1. It had a 0 response time for the first time, but then it had to wait for 4 milliseconds over there. And you can add them up or, write them so that you make sure you don't make a mistake. So, I'm going to write them down here. So, initially it was 0. Then from 12 to 16, that's another 4. So, I'm going to add this up and then 4. And then from 16 to 28, that's 12 more. So, added by 4, that makes it 16. And then from 32 to 41, that is 9 more milliseconds. Added to the 16, that's 25. Okay, so the wait time for process 1 is 25. Process number 2. Initially, it had a response time of 3, and then it waited from 12 to 20, which is 8 milliseconds. Added to this, that makes it 11. And then from 24 to 36, that's another 12. Added by this, that makes it 23. And then it waited from 40 to 47, that's 7. Added by this, that makes it 30. P3, initially it had a response time of 6. P3, where is that? Okay, so there. Now, from 20, it waited till 32. That's 12. So, you add 12 to this 6, you get 18. Then, it waited from 36 to 45. That is 9. And you add it to this, and that makes it 27. For process number 4, initially it had a response time of 9. Right there. And then it waited from 28 till 40. That is 12. 12 by this 9, you add it up, and that makes it 21. It does not have, I mean, it's finished there, so there's no more. So turnaround time, again, it helps to verify your calculations, to calculate your turnaround time two-way. So from the chart, the burst time and the wait time. You remember, wait time and service time. You add them up, 45. You add these up, 45. You add these up, 37. You add these up, 26. Now, have we calculated them right? Remember, finish time minus arrival time. Is that the same or not? Let's see. Process number 1. Finished right here at 45. It arrived at time 0. You subtract that and you get 45. So that's good. Process 2. It finished right here at 50. It arrived at time 5. So you subtract that and you get again 45. So that's good. P3. It finished at 47. It arrived at 10. So that's 37. And again, we got it right this time. P4. It finished 41, it arrived at time 15, so that's 26 when you subtract it. Don't look at this, actually subtract it to make sure you don't make a mistake, and then compare, right? So we got them right, and now this is one of the scheduler in this question. So let's do an average on them. I am just going to use a different one here. So we have round robin, the response, wait, turnaround. These are average numbers. So for round robin response time, you add them up, you get 3, 9, 18 divided by 4. That's 4.5 milliseconds for response time. Wait time, you get 25 and 30, that's 55. 55 and 27, that's 82. And with this, that's 103 divided by 4. That's 25.75, I suppose. Turnaround time, 45 and 45, 90. 90 and 37, that's 127. 127, and this, that's 153. 153. You divide it by 4. Well, let's make it. It will be. If we want to do it. 38.25, right? I suppose it's correct, but it doesn't matter. A lot of the cases actually in the exams or questions, there will be, you have integers, or, you only have to care about so much. Usually you don't have to end up calculating, decimals. So this is with the round robin. So now we can do another example with another one. So, for example, let's do with the priority. So priority, I am just going to replace these. Actually, I'm going to use this one. Oh, this is fixed. Okay. So for priority, okay. So for priority, I'm gonna you start a different Gantt chart. We are now doing priority, and we're going to do it with preemption. Preempt. Why? Because it's a little bit more difficult, and it usually covers the non-preemptive. All right. So for the priority with the preemption, you have to take again into account the arrival times, because that's where the preemption happens, right? So at time 0, you only have process number 1, so it gets scheduled, right? So P1. Does it get finished or not? It wants to run for 20 milliseconds. Before that, P2 comes at 5, right? So let's see. At 5, P2 arrives. What is the priority of P1? 3. What is the priority of P2? 1. P2 has a lower number priority, which means a higher priority. So P1 should be preempted and P2 should get scheduled at this time. So P1 gets scheduled out. You can write down the remaining time. So it had ran for 5 milliseconds. It was initially 20, so 15 is left. P2 has arrived with burst time of 15. It gets scheduled and runs. So what happens is that it wants to run till time 20. At time 10, P3 comes with the burst time of 10. What is the priority of P3? P3 has the priority number 2. We are running P2 with priority number 1. So the new process has a lower priority. So we don't have to preempt the currently running process, and we keep running. We keep running till 15, where P4 comes. P4 arrives with the priority 4, which has the lowest priority. So again, we don't have to preempt it, and we keep running. From here on, it's basically like non-preemptive. Because we should take a look at the process and let them finish. So P2, for example, gets scheduled here, and it should run for 15 milliseconds. Starting from 5, it runs all the way to 20. And then it will be done. Actually, I'm just going to cross it on itself, right? So then amongst the rest of the processes, which one has the higher priority? The lower number has P3. It should run for 10 milliseconds. So from 20 till 30, it will run, and then we'll mark it up. And then again, from the rest of the processes, P4 and P1. Which is the higher priority? P1 has the smaller number, right? So then it should get scheduled. For how long? We have kept the remaining time here. For 15 more milliseconds, P1 gets scheduled here till 45. And then P4 finally gets scheduled once we mark it out. And it will, see, there's a mistake. The 4 is the priority. Read it from the right column. And the remaining time is 5. Now, if we did the mistake, then we would actually finish at 49. And then if you check the burst time, then you know that you made a mistake. A simple mistake as that can be corrected easily by adding them up. P4. Okay? So now the schedules look like this. So P1 got scheduled, then got preempted by P2. P3 was higher after P2, so it got scheduled, and then P1 continued, and then lastly P4, right? So this is simple. I forgot this doesn't move. Now this comes down. Okay, now I didn't think about this. Okay, so let's calculate the response times, and then I will write them down. So for P1, the response time is basically from the arrival time till the scheduled one, so that's 0. P2, it arrived at 5, it got scheduled at P5 at time 5 again, because it was of a higher priority, right? So the response time is 0. P3, it arrived at 10, it got scheduled at 20, so that's 10. P4 arrived at 15, and it got scheduled at 45, so the response time was 30. The wait time, P1 initially didn't wait, but then had to wait from 5 to 30, so that's 25 more. P2 started here and then finished, so there is no more waiting, and it had a 0 response time, so that's already 0. For P3 and P4 also, they started and then finished, so the response time and wait time should be equal, 10 and 30. So if you want to calculate the turnaround time, it's going to be, again, the same thing. Either the burst time and wait time together. So let's see. 45, 15, 20, 35. Or you can also see when they finished minus their arrival. So take a look. P1 finished at 45. It arrived at time 0, so that's 45. P2 arrived at 5. It finished at 20, so that's 15. P3 arrived at 10. It finished at 30, so that's 20. And process number 4 arrived at 15. It finished at 50, so that's 35. So seems to be fine. Now let's do the averaging. So response time in this case is 40 divided by 4. That makes it easy. 10. See, already the response time for round robin is relatively smaller. So this is priority preemptive. Wait time, 25 and 35, 65 divided by 4, that makes it 16.25. And then the turnaround time, 60, 80, 115. 115, that's 28.75, right? And so then we're going to go for the next one. So the next one, okay, now I have my computer kind of stuck. Okay, I'm just going to start with something. Let's go with shortest job first. Okay, this is a little bit easier than the shortest remaining time. We already did the shortest remaining time, so shortest job first. So remember, in the shortest job first, again, we don't care about the priority. Actually, since we did the priority, let's compare it. What if it was not preemptive? Let's do it right here, just because they're pretty similar, and then we're just going to do it. So if it was not preemptive, when process number 1 got scheduled, it just goes on till it finishes, right? So process number 1 had a burst time of 20, so it runs all the way till 20, right? And by the time 20, what has happened? At time 5, we have P2. At time 10, we have P3. And at time 15, we have P4. So by this time, we already are done with P1. And then we take a look. At this time, what is the next priority after P1 is gone? Well, the highest priority is P2. So P2 gets scheduled here. And again, it does not get preempted. It runs all the way till it finishes for 15 milliseconds. 35 finishes. After that, P2 is finished. Again, between P3 and P4, well, P3 has a higher priority with a lower number, so it runs for 10 milliseconds, so that's still 45. And then P4, it runs for the 5 millisecond that it wants till 50. So it's just like, much simpler. And if you want to calculate the wait time and the response time, again, because they don't get preempted, so the response time and wait time will be equal. So for P1, both of them will be 0. And the P2 from 5 to 20, that's 15. And for P3 from 10 to 35, so that's 25. And for P4 from 15 to 45, that's 30. And for the turnaround time, you can just add them up again. 20 and 0, 20. 15 and 15, 30. 10 and 25, that's 35. 5 and 30, that's again 35. And if you want to average them with non-preemptive priority, so you just have 40 and 30, that's 70 divided by 4. 17 and a half. The same goes with the wait time. And the turnaround time is 50 and 70, that's 120. so 30. Okay? And, well, this was, sorry, here I made it, I mean, it was clear. It was non-preemptive priority. Okay? If you want to take a look at this, and I am going to clean the other one. In the meantime, I'm going to push it up. I'm not going to use this. Bring this down. All right. So next, we're going to cover shortest job first. All right. So the shortest job first, non-preemptive. Again, usually the non-preemptive ones are simpler. So we're going to start at time 0. There's only P1. P1 got scheduled, and because it's non-preemptive, we already know that it goes till 20. By the time 20, we have P2 with the burst time of 15. We have P3 with the burst time of 10, and we have P4 with the burst time of 5. So, sorry. At this point, the shortest job is before, and before gets scheduled for 5:25, and then P3 has shortest job, so P3 gets run for 10 milliseconds till 35, and then P2 gets scheduled for 15 milliseconds till 50, right? So that seems simple, but let's take a look at the numbers. Response time, P1, 0, as well as wait time. Remember, for the non-preemptive ones, they will be equal. P2 arrived at 5, it got scheduled at 35, so that's 30. P3 it arrived at 10, it got scheduled at 25, so that's 15. P4 it arrived at 15, and it got scheduled at 20, so that's 5. Turnaround time, add these up, 20 and 0, 20, 15 and 30, 45, 15 and 10, 25. 5 and 5, that's 10. Double check. 20, negative 0, 20. 50, negative 5, that's 45. 35 minus 10, that's 25. 25 minus 15, that's 10. So it looks fine. So if we want to average them now, response time is 50 divided by 4. That's shortest job first, again, non-preemptive. What was that? 50 divided by 4, that's 12.5. The same goes with the wait time, 12.5. The turnaround time, on average, is 20, 65, 90, and 100. So that's 25. See, it's smaller than the rest. The shortest remaining time first, it can be even less than that, right? And yeah, so that's the shortest job first. Now, take a look at the shortest remaining time first and see how it improves this. It starts similar to this, but it does not continue the same. So P1 gets scheduled here, but it does not run to the 20th millisecond because at the time 5, something might happen, right? So at time 5, P1 has the remaining time of 15, and P2 arrives also with the burst time of 15. So actually in this example, notice they will all have a tie. And when you have a tie, usually it should be given to you in the question. So if you want to keep the P1 running, because technically it's not smaller than the running process, so we don't want to go through the overhead of it, scheduling it in and out for extra, we let P1 just run, and so at time 10, P1 will be 10. Now we'll have like P3 again with 10. If we want to be consistent, so we should not schedule P1 out. We should not preempt it and let it run till 15, which then P1 reduces to 5 remaining time, and P4 arrives with the remaining time of 5. So again, if we don't want to preempt it, it will just run, and it will basically be the exact same example as shortest job first. So in this example, preemption actually does not help. And even if you decide to preempt P1 to P2, let's do it that way and see what happens. Usually that's not the case. When there is a tie, I think it should be given to you in the questions, but it kind of makes sense to avoid the overhead and keep the currently running process running. But let's see. If we're going to take it like that, what it's going to look like. So at this point, if we want to schedule P2 in, so the shortest job first, basically, if we don't do the preemption with in a tie situation, it's going to look exactly like shortest job first, right? So that's why that's the only reason I'm doing it this way, just to see, what's the difference. So at time 10, P2 comes down to 10, and then P3 also arrives at 10. Again, in the same situation as of a tie, we give priority to the new process, so P3 gets scheduled, and then it runs till 15. It goes down to 5 more milliseconds, and then P4 arrives with the 5 milliseconds of burst time. Again, we allow that. And then from here on, we don't have any arrival. So this runs for 5 milliseconds till 20. And then from here on, P3 has the shortest time. So P3 gets scheduled in for 5 milliseconds. So that's 25. And then this will get marked. P2 has 10 more. So this runs for 35. And then P1 has 15 more. So that goes on till 50th millisecond, right? So let's take a look at the numbers in this one, in this example. So I'm going to write it down here. Shortest remaining time first. Preemptive plus tie. This is not a term. I'm just writing it down just to remember, right? So the response time for P1 is 0. For P2 is also 0. For P3 is also 0. And for P4 is also 0. Because whenever they arrive, they preempted the running thread and then scheduled them. But the wait time is going to be different because they have waited. So P1 has waited from 5 to 35, so that's 30. P2 has waited from 10 to 25, that's 15. P3 has waited from 15 to 20, that's 5. P4 has not waited, it's just like finished. And the turnaround time, again, burst time plus wait time, so 50, 30, 15, and 5. Right? So let's take a look at the numbers. We can also check this again. Turnaround time, 50, negative 0, that's 0. For P2, 35, negative 5, that's 30. P3 from 25, negative 10, that's 15. P4 is just like 5, so this should be fine, right? Now, response time average is 0. Shortest remaining time first is basically, also expected to have a short response time in this case because we scheduled them immediately. The wait time, we have 30, 45, 50 again divided by 5, so that's basically the same. Again, because they were the same amounts of, so there was either P1 had to wait or P2, it didn't matter. And whenever one of the processes was waiting for a shorter process, they had to wait anyways. In the case of a tie, again, because they were in a tie, either this process had to wait for the same amount of time and that the other one. So the result will be the same. The turnaround time is like 80 and then 100, again 25. So it didn't matter because remember the wait time and the burst times are the same. So it's either one process or the other one. So in this case, in this example, shortest time, remaining time first does not actually. And again, this is it's a non-normal case of a shortest remaining time. So I think we also covered. We're going to cover first come first serve, right? I think that's the only one that we have not covered. I'm just going to wipe these. And we're going to do it first come first serve, which is relatively simple. So times 0, first come, that's P1. So P1 gets there. There's no preemption, so it just keeps running for 20 milliseconds. And after that, within this time, here P2 has arrived, here P3 has arrived, here P4 has arrived. So if you want to take it a first come first serve, after this basically it's going to be the turn for P2. P2 keeps running for 15 milliseconds, so till 35, and then P3 keeps running for 10 milliseconds, so that's 45, and then P4 keeps running for 5 milliseconds till 50, right? So these are the numbers, and let's take a look at the table. All right. So for P1, arrival is 0, schedule 0, response time is 0. It didn't wait. Again, preemption is not there, so wait time and response time is going to be the same. P2, it arrived at 5. It got scheduled at 20, so the response time and wait time is going to be 15. For P3, it arrived at 10. It got scheduled at 35, so that's 25. And finally, for P4, from 15 to 45, that's 30. And then we add them up, 20 and 0, 20, 15 and 15, 30, 10 and 25, 35, 5 and 30, again 35. Let's double check them. Turnaround time for P1, from 20 to 0, that's 20. P2, 35, subtract 5, that's 30. P3, from 45, we subtract 10, that's 35. For P4, from 50, we subtract 15, and we get 35. So far, so good. How about the averages? For response time, we have 40 and 30, that's 70, divided by 4, that's 17 and a half, I suppose. For wait time, it's going to be exactly the same. And for turnaround time, that's 50, 85, 120, so that's 30. All right? And so this kind of went to sleep for itself and then rebooted. So this question, I think we didn't miss any other part of the question. I just want to double check with the slide. So first come first serve, shortest job first, shortest remaining time first, round robin, priority, preemptive, and non-preemptive. So yeah, that basically sums it up. If you take a look at them, relatively the round robin gives a overall short time. But the turnaround time is pretty bad. The priority, it depends, again, how the priority is defined. Shortest job first and shortest remaining time first. Again, this case is kind of not the normal way, but overall, their turnaround time is going to be minimal compared to the other ones. And the first come, first serve, it depends. So in this case, for example, because the first process was the longer one, so it had a bit of a convoy effect. So that's why the turnaround time is like larger, and also the wait time is relatively large, or the response time is also large. Again, these are because of the convoy effect. All right. So I hope this exercise kind of sums it up, and how to approach the Gantt charts, how to verify your solution, as well as do the calculations. And so usually they are not this long. Question does not ask for all of them, but basically you should be able to solve all of the different type of algorithms on all the examples. All right. See you in class.